Greetings everyone, we are the students from UTAR University Tunku Abdul Rahman and we are from the Faculty of Engineering and Green Technology. Our course is Petrochemical Engineering and this is our capstone project titled Production of 1,3-butadiene from Heavy Naphtha using fluid catalytic cracker and extractive distillation. We will now begin with the introduction of each of our members.
My name is Chu Eng Yong.
I'm Elson Lau Hong Sheng.
And my name is Jonathan. And due to some unforeseen circumstances, our fourth group member will not be with us today. I will proceed with the fifth group member.
Hello, my name is Yajun.
In this project, there are a few objectives that we would like to achieve. Firstly, to study the technologies in 1,3-butadiene production, to evaluate the profitability of 1,3-butadiene production, to design a chemical plant using standard procedures and estimate the production unit cost in order to evaluate the plant design, to be able to compute approximate profitability measure and ROI, to estimate annual costs in order to determine the total capital investment cost.
My name is Yajun. I will start with Chapter 1, Literature Review and Project Conception. The characteristics of 1,3-butadienes are: it is a colorless gas with hydrocarbon oil at standard temperature and pressure. It is a hazardous chemical due to its flammability, reactivity, and toxicity. It is commonly used in the production of synthetic rubbers. Over 95% of butadiene is produced as a byproduct of ethylene production. Crude C4 stream is separated from the other C4s by extractive distillation. Extraction solvents such as dimethylformamide or acetonitrile is used for the production of high-purity 1,3-butadiene. Heavy feeds such as naphtha use higher amounts of C4s and butadiene. The 1,3-butadiene capacity is determined by an ethylene cracker operating rates, the type of feed being cracked, the availability of butadiene extraction capacity. United States is the most significant crude C4 net importer. Largest net exporters of finished butadienes are Canada, Western Europe, Saudi Arabia, and Korea, while the largest net importers of finished butadiene are Mexico, the US, and China. Butadiene is used for the production of tire, polymers, and petrochemical intermediates. The application of butadiene-based products are automobiles, construction materials, appliance parts, computers, telecommunications equipment, clothing, protective clothing, packaging, and household articles. The figure indicates the amount of naphtha produced in 1,000 metric tons in Malaysia from the year 1990 to the year of 2014. The year with highest naphtha production is in the year of 2007, where the production reached 4,184,000 metric tons in that particular year. The production of naphtha in Malaysia never hit the peak after the year 2007. From the figure shown, Malaysia is only contributing a very small part in producing naphtha compared to the rest of the world. Malaysia only has a world share of approximately 1% and is currently ranked number 27. The table shows the price of naphtha in the European market in the last 10 days as on June 14, 2017. From the data analysis, it shows that the changes of naphtha price is not that huge for the past 10 days and is considered as stable. From the graph, it shows the market price of butadiene and PBR from July 2016 to May 2017. In March 2017, the price of butadiene hit a 56-month high at the selling price of $3,070 per metric ton. The increment in the price is believed to be caused by the tight supply of the butadiene. In the same time, the strong demand of the butadiene to be used as a feedstock in producing styrene butadiene rubber, SBR, SB latex, and acrylonitrile butadiene styrene also contribute to the increment of butadiene price. The limited supply of butadiene is partly caused by the continued increase in car sales in China, which results in higher demand of tires and also the reduced rubber output due to the flooding in Thailand. However, the price has dropped since March, and the price of butadiene is at 1,295 tonne as of 5th of May. The price of butadiene is also expected to drop in the future. The site study is an essential preparation for the setup of plant to minimize the production cost and inconvenience factors, at the same time maximize profit at its potential market. The general factors that are taken into the consideration are the availability of raw material, transportation facilities, availability of manpower and utilities, industrial infrastructure, effluent disposal, and also local community and nature consideration. The industrial location set for our project is at the Tanjong Langsa Industrial Estate, 81700 Pasir Gudang, Johor. There are numerous factors taken into the consideration as aforementioned. For availability of raw material, Petronas from 8 km away act as the naphtha supplier. For the transportation facility, Tanjong Langsa port from 1.5 km away can act as the import or export port for the 1,3-butadiene synthesis. For the availability of manpower and utilities, there are local community from 3.8 km away for manpower, while the YTL Pasir Gudang Power Station from 18.5 km away provides power source. For the industrial infrastructure, JP Nelson Malaysia from 7.2 km away could act as the machinery repair and service center. For effluent disposal, Kemalaya Sendirian Berhad from 7.9 km away provides chemical waste management, while Southern Strength Sendirian Berhad from 8.5 km away provides scheduled waste recycle. For the local community and nature consideration, the nearest rural area locates at 16.4 km away from the targeted land. Therefore, the operation of 1,3-butadiene synthesis plant would not bring huge impact towards them. For the process selection, cracking process is an operation that breaks heavy or large compounds or molecules into smaller and lighter compounds. The common thermal cracking methods are delay cooking, which could improve and transform petroleum residue into fluid, leaving solid concentrated petroleum coke, and also the pyrolysis cooking, which utilize steams to produce light components and compound. In conventional pyrolysis cracking, the heavy hydrocarbon is break into light and unsaturated hydrocarbon with the employment of high temperature steam. Butadiene is one of the core products in ethylene synthesis and is obtained through the recovery process of butadiene purification. Two radical steps are involved in this cracking process. First, the initial formation of paraffin and olefins from primary cracking reaction, followed by the olefins-rich light products formed from secondary cracking reaction. The catalytic cracking process is an alternative cracking process to overcome the high operation cost of pyrolysis cracking process. There are two catalytic cracking methods, which are the fluid catalytic cracking and also the hydrocracking. The presence of catalyst speed up the reaction without affecting the reaction equilibrium. The fluid catalytic cracking, which is also known as FCC, process in the fluid phase. It comes with a multiple choice of catalysts, such as aluminium chloride, alumina, and also zeolite. Hydrocracking converts low quality feedstock into high qualities. The advantages are low investment option and also environmental friendly. The hydrocracking bifunctional catalysts have cracking function by the acidic side of catalyst and also the hydrogenation and dehydrogenation function provided by the metal in catalyst. The hydrocracking reaction involves the splitting of CC bond or CC rearrangement reaction, which is also known as hydroisomerization process. The fluid catalytic cracking process is chosen over pyrolysis cracking process due to numerous reasons. First, the high construction cost and investment for pyrolysis cracking process. This is due to the pyrolysis furnace are larger than the FCC reactors. Next, FCC process improves the contact surface and control of heat transfer efficiency with the combination of multiple systems in FCC. Last but not the least, the ability to employ catalysts in the cracking process of FCC. For example, zeolite or metal oxide catalyst. There are three factors of energy saving. First, usage of catalyst to lower the activation energy for CC bonding rupture. Next, the presence of catalyst contributes to better quality chemical reaction, improving selectivity to desired reaction route, and also the ease of catalyst regeneration to improve the overall reaction efficiency and catalyst span life by the removal of cork. Dimethylfuramide solvent extraction process is chosen. This is because it comes with the advantages of NMP and its water mixture are non-corrosive and non-fouling. It is the least toxic solvent that is easily treated by conventional biological degradation, thus is environmental friendly. The NMP is also flexible to process all industrial C4 feeds regardless of their 1,3-butadiene content. Carbon steel is used for the construction of the entire unit. This is because it is stable, non-reactive, and also cheap for the construction cost. The efficient heat recovery system and optimal process design lower the operating costs. Let's proceed to the chapter 2 of process synthesis and process flow diagram. The heuristic is introduced to obtain the highest possible yield in the safest way. There are 4 possible process synthesis approach and heuristic. For the heuristic 1, it suggests the separation with the smallest relative volatility loss, which is also known as the azeotrope case. However, heuristic 1 is not suitable for this process. This is because the azeotrope compounds of C1 and C2 are to be separated at the very beginning of the process with the help of demethanizer and deethanizer. In heuristic 2, it's a direct sequence separation. More volatile component has higher removal priority. The increasing number of carbon result in the raise of boiling point. Therefore, C1, C2, and C3 are first removed from C4. In heuristic 3, it suggests the removal of largest fraction of component. It is the following separation process due to decrement in volume when going through the distillation column. However, it requires additional heat control, unsuitable in long-term production. The last heuristic, which is the heuristic 4, it favors the near equimolar speeds. However, separation in terms of molarity does not benefit as much as the separation in terms of boiling point, since the hydrocarbon in naphtha are heat sensitive. In this slide, we will be presenting the ion model for the process synthesis approach. This is our complete process flow diagram with control system included in it. Reactant will react in fluidized back catalytic cracking unit. Product of reaction will undergo series of separation process to obtain the pure 1,3-butadiene. All byproduct is purified and was sold to generate extra income for the project. First of all, feedstock heavy naphtha will flow into furnace through stream 1, labeled as S1. Inside furnace, feedstock is heated to the process temperature, which is 850 Kelvin, so that cracking processes have enough energy to take place. Next, hot feed will flow into the fluidized back catalytic cracking unit through stream 2. Inside FCC unit, heavy naphtha is cracked into many different types of lighter hydrocarbons such as C1 to C5, methyl acetylene, product 1,3-butadiene and large amount of hydrogen. products will flow into cooler so that all of it can undergo condensation except hydrogen. Temperature of product is cooled to 20.25 Kelvin so that only hydrogen remains in vapor phase while other products are melted. Inside flash drum, hydrogen is removed into top stage as vapor while other products will escape flash drum through S6 to heater. The role of heater is to increase the temperature of products to the boiling point of propane. With the increase of temperature, methane, ethane, and propane can be removed as the top product in the propanizer. But before going into the propanizer, products are compressed into compressor to increase pressure for the ease of separation process in the following distillation column. As mentioned just now, methane, ethane, and propane will exit as top product in the propanizer. Other products will exit the propanizer as bottom product and flow into the butanizer through stream 10.
In the butanizer, hydrocarbon with 5 carbons or more will exit as bottom product, while other remaining products such as butene, methyl acetylene, and 1,3-butadiene will flow into extractive distillation column through stream 11. In extractive distillation, solvent NMP is introduced to separate butene from methyl acetylene and 1,3-butadiene. The full name of NMP is N-methyl-2-pyrrolidine. It is a very famous solvent in conventional 1,3-butadiene production in many industries. Butene will exit as top product in extractive distillation as it is a lot less soluble in NMP compared to methyl acetylene and 1,3-butadiene. Remaining 2 products will flow to rectifier through stream 15. Inside rectifier, NMP will exit as bottom product as rectifier temperature is set to the boiling point of methyl acetylene. Only 1,3-butadiene and methyl acetylene exit as the top product of rectifier and flow into the last component, which is distillation column. In the last distillation column, temperature of 260 Kelvin is set to facilitate the separation process. 1,3-butadiene will exit as top product while methyl acetylene exits as bottom product. Pure 1,3-butadiene is obtained at the outlet stream of last distillation column, which is stream 18.
The figure shows the development of 2D plant layout, while this figure shows the development of 3D plant layout.
My name is Elson Lau and I will talk about Chapter 3, Material and Energy Balances. I will start with the material balance. Firstly, the data for the components inside the feed stream. Our feed, heavy naphtha, consists of several components such as heptane, octane, nonane, decane, and undecane. The composition, molecular weight, density, composition times molecular weight, and composition times density data are all recorded in this table for each of the components. These data will later be used in the calculation for the material balance. The feed, heavy naphtha, will be cracked into lighter products by the fluid catalytic cracker. In this project, we assume that the conversion rate in the fluid catalytic cracker is 100%. The lightweight products that were cracked consist of methane, ethane, methyl acetylene, propane, 1,3-butadiene, our product, butane, pentane, and also hydrogen. The output rate, which is in kilomole per hour for each of the product, is recorded in this table. This table consists of the molar flow rate of material and product in each of the stream in our process flow. The main product in this process, 1,3-butadiene, can be found in stream 19, which has a molar flow rate of 56.0276 kilomole per hour. Next, we will proceed to energy balance. This table shows that the specific heat capacity of different components at different temperature. These values are to be used in the calculation for the energy balance. Next, in this table, the heat of vaporization of different components are recorded. The heat of vaporization is also used to calculate the energy balance. The following few slides will show the sample calculation for the enthalpy change in our first unit, the furnace. The enthalpy change we calculated for the furnace is 23.13 gigajoule per hour. In this table, it shows that the energy change or the enthalpy change for each of the units that we have calculated. In previous slides, the value that we have calculated are calculated manually by our team members. In this slide, the table shows the heat and material balance table from Aspen Plus.
My name is Chu Eng Yong, and I will be covering Chapter 4, which is Process Integration, Optimization and Waste Treatment. First of all, process integration. In this project, one cooler and one heater is used. We have integrated the heat exchangers network to achieve the maximum heat recovery for the process. This integration process can help us to save unnecessary utility costs for this project. As shown in figure, temperature of product reduced from 900 Kelvin to 20.25 in cooler and increased from 20.25 Kelvin to 223.15 Kelvin. The amount of heat absorbed by the cooler is near to 3000 kilowatt, while heat across the heater is only near to 400 kilowatt. This means that the amount of heat absorbed in cooler is much more higher than the heat needed in heater. Heat energy is transferred from cooler to heater to save utility costs required for the heater. The remaining heat of approximately 2600 kilowatt that can be used in the production line is used in other appliances inside the factory. Next, in the section of optimization, linear programming method is used to achieve the objective function. Objective function of this project is set to be net profit per day, with the listed cost of raw material, of utilities, labor, and the selling price of different products. Computer software such as Excel solver is used to find the maximum profit per day this project can yield. As shown in this table, highlighted green cell shows the profit source of this project, which is through the selling of various products. Highlighted red column cell shows the cost of this project. The maximum net profit we can get from this project is 89,897 USD after considering the cost of raw material, labor, and the utilities after the process integration. As shown in this sensitivity report of optimization, the best operating hour is 24 hours per day as it can yield the maximum profit. Reduced cost of this project is 3,745 and 69 USD, which means that for every 1 hour of downtime of this project, the loss of profit will be 3,745.69 USD. Lastly, funding of 500,000 USD is needed before the starting of the project. Next, waste treatment. Byproduct and waste generated in production line needed to be treated and sold. Products generated in reactions other than 1,3-butadiene is considered a byproduct or waste. First of all, spent catalyst from reaction need to undergo pre-treatment before it gets sold. A pre-treatment is required to eliminate some of the hazardous compounds attached to the surface of catalyst. Zeolite catalyst is less harmful to the environment after treatment, such as metal recovery. Hydrometallurgical extraction process is used for this treatment. In this treatment, zeolite catalyst will first be leached to remove the compound on the surface. The solution of leaching process is concentrated and disposed through incineration. Zeolite catalyst after treatment will be sold to Simalaya Sdn Bhd, which is a fertilizer manufacturer, located 7.9 kilometers to the northwest of the selected site. Next will be the capturing of hydrogen in phase drum. Hydrogen need to be captured in outlet stream of phase drum. Vacuum pump is used to transfer hydrogen to hydrogen tank as shown in figure. The materials used for the construction of hydrogen storage tank must be rigid enough to resist the outburst of highly pressurized and compressed hydrogen gas. Methane, ethane, propane, butane, pentane, and methyl acetylene need to be purified and stored in cylinder tanks. First of all, gases from different distillation columns is extracted with the usage of vacuum pump to storage tank of each stream. Separation process is needed to separate the mixture of gases into pure gas. For the separation process, turbo expander is employed because it is the most economical process in the present day. In this process, chill gas is expanded through a turbine, reducing the temperature to about -100 degrees Celsius for a separation between methane and other gases. At this temperature, gaseous methane can be separated from the liquefied ethane and heavier hydrocarbons by distillation. Components with lower boiling point will be separated first, followed by the component with higher boiling point. For separation of other gas, temperature is adjusted to the boiling point of each component. At the boiling point, component that intended to be separated will be in gas phase, while other heavier product will be in liquid phase. Finally, gases will be compressed and stored in cylinder tank and sailed through Tanjung Langsat port. The next waste, which is the last one, NMP solvent. NMP from rectifier is fed to solvent degassing section. The solvent is heated with steam under vacuum condition in a regeneration vessel. Remaining of hydrocarbons is removed. Hot strip solvent from the bottom of the degasser will pass through a heat economizer before going back to extractive distillation column for reuse purpose.
Next, we will now proceed with Chapter 5, Equipment Sizing and Cost Estimation. Firstly, we will start with the design specification of the furnace. The furnace functions to provide heat via the combustion of the fuel. It comprises of internal components such as wall lining, tubing, roof, and piers. The material chose for the external of the unit is steel. Due to its ability to remain its strength at high temperature, good resistance, ability to high heat, and good heat insulator. The material chosen for this unit's internal is fire brick. Due to its ability to withstand high temperature, high mechanical strength, lightweight, and low cost. The next design specification is the fluidized catalytic cracking reactor. The catalyst used for this reactor is the zeolite catalyst. The material chosen for this unit is the grade 410 stainless steel, due to its ability to withstand high temperature and corrosion. The chromium within the stainless steel has a resistance towards oxidation, and it has low cost. Catalysts that have become deactivated by coke formation is reactivated by burning off the coke in the catalyst regenerator. Grade 410 stainless steel is chosen for the catalyst regenerator due to its ability to withstand high temperature in the regenerator, and it also prevents corrosion that might cause by the presence of oxygen. The next design specification is the refrigerator. It functions to remove heat or lower down the temperature of the component using a coolant. The material chosen for the exterior cabinet of the refrigerant is aluminium, due to high strength, and it will not deform easily. It also does not absorb any sort of energy, so that no extra heat energy is added or removed. It also has high thermal conductivity. The inner of the cabinet is usually made of the same material as the exterior of the cabinet. The insulation layer, polyurethane, is placed between the exterior cabinet and inner cabinet. Because of excellent insulator, it is cost effective and structurally strong. The inner part of the refrigerator consists of the cooling system with refrigerant running in it. The function of the flash drum is to remove hydrogen stream. Low alloy steel is preferred as the material of construction because of the presence of chromium and molybdenum in the alloy steel that can resist corrosion. Chromium also improves the anti-oxidation and anti-corrosion ability. Molybdenum enhances its strength in high temperature conditions. The function of the heater is to convert energy supplied by a source of heat energy in a closed and insulated environment. The material used for construction of the heater is aluminium. Due to high resistance to chemical corrosion and erosion, as well as high heat durability and grip strength. Magnesium oxide is used for the insulation layer because it has excellent heat transfer capability, high temperature tolerance, superb durability, and precise heat control. Nichrome is used as a heating element as it has much lower operating temperature than the temperature limit of mineral insulated heater. The function of the compressor is to transfer mechanical energy to the pressure or kinetic energy. The material selected is chromium molybdenum alloy steels, as it can endure the high chemical resistance, withstand high temperature, pressure, and speed of the process. It can also withstand high hardness and toughness and high tensile stress. The next design specification is the distillation column. It functions to separate components from a mixture of product stream. The material used for the surface of column is stainless steel due to high resistance to chemical and high resistance to the oxidation and corrosion. The trays chose is sieve tray for the distillation column with carbon steel. Due to low cost and it is widely available, good tensile strength and hardness, non-reactive and non-combustible, as well as resistance to high pressure.
Next, I'll proceed with the cost estimation for each of the major equipments. This table consists of the molar flow rate, molecular weight, density, and volumetric flow rate of each of the components present inside of the catalytic cracker. These values are used to determine the dimensions of the equipments. After the volume of the reactor, length, diameter, design pressure in the column, wall thickness, and a weight of FCC is calculated, the cost estimation calculation starts. The following slide shows a sample cost estimation calculation for the fluidized bed catalytic reactor. After we done the calculation, the final cost of this FCC reactor we recorded is about $3 million. The cost of each of the major equipments that we have calculated is recorded in this table. Next, the cost estimation for storage tank. We have a total of 18 storage tanks to store our products. The total cost of this storage tank is around $14 million.
My name is Mr. Lin Huang Hong. Now we will proceed to the Chapter 6 Process Control and Safety. The primary objective of using instrumentation and control scaling in this project are safe plant operation, maintain production rate, maintain product quality, and saving costs. Some basic control systems are integrated to cascade control system. Cascade control provides smoother control in such case, and the direct control of the variable will lead to the unstable operation. In its project, multiple control systems were employed, which are temperature control. Secondly is the pressure control. Thirdly is the flow control. Next is the level control, and finally is the spare time for safety purposes. Flow, pressure, temperature, and composition are the four important process parameters in the hydrostaticity of FCC unit. For example, in case of the parameter of flow, four possible variations of issues could have occurred. In such case, with no fit inlet flow, it is possibly caused by control valve short, failure of inlet valve, and leakage or blockage of pipe, which will lead to consequences such as operation value, reaction stop, and overheating in reactor. Possible action to be taken in order to solve the problems mentioned are installation of flow meter, installation of backup pipeline, and request emergency stop. In case of more free inlet flow, the possible causes are failure of inlet valve and too much pressure inside pipeline. It will lead to consequence of occurrence of flooding in reactor and reaction stop, wastage of raw material. In order to solve this issue, installation of flow meter is necessary or to open the spare tank valve. In the case with less free inlet flow, it is possibly caused by failure of inlet valve, leakage or blockage of pipe, or pump failure. Consequences such as low amount of product output or overheating in reactor are possible. Therefore, installation of flow meter or installation of backup pipeline are the solution to this particular problem. Reverse free inlet or outlet flow is also one of the possible problems that will occur in real-life situations. It will cause failure of inlet valve, failure of outlet control valve, or pump failure, which will bring the consequence of operation failure or raw material misreproducts. To troubleshoot this issue, installation of check valve as a prevention and pressing emergency stop as a solution. For other process parameters of FCC unit, kindly refer to the presentation slide, where much more hydro study for different particular units with clear elaboration could be studied from the project. In Chapter 7, we will be discussing about the mechanical design and specification of the industry that we use. Let's start with the dimension of the units. The length, inner and outer diameter, volume, and weight of each major unit can be found in this table. Now, let us proceed to the section showing the engineer drawing of units. This figure shows the side view of the fuel catalytic cracker unit, which consists of a fuel catalytic cracking reactor and a catalyst regenerator. The dimension of its unit are also shown in the figure. The next figure is the side view of the flush drum. The following figure shows the side view of the distillation column. The dimension of the decomponizer is shown in its figure. The side view of other distillation columns such as the decomponizer and the extractive distillation and other units are the same as this, but with different dimensions. The full drawing of each unit can be found in the printed report.
My name is Jonathan, and I will be presenting on Chapter 8, which is Profitability Analysis. The main subtopics to be covered in this chapter are total capital investments and payback period or return on investment. This is the total cost of both major and auxiliary equipment. The calculations of cost for major equipment were calculated in the previous chapter, and the cost of auxiliary equipment, which includes the furnace, cooler, heater and compressor, are calculated in this chapter. The cost of both major and auxiliary equipment are added, and the total bare module cost for the 1,3-butadiene production plant is 42.8 million. However, this figure is rounded up to 43 million to allow for flexible changes. This is a summary of total capital investment. Firstly, the direct costs consist of mainly equipment costs, site development costs, as well as auxiliary facilities and other costs. Equipment costs consist of the cost of major and auxiliary equipments, which is 43 million. For site development, it's assumed that the cost required is 30% of the total bare module cost of the equipment, which is 12.9 million. The cost of auxiliary facilities and other costs are assumed to be 10% of the main plant, which amounts to 4.3 million. The added value of these three direct costs would be 60.2 million. This direct cost is then added to both contingency and contractors' fees, as well as engineering and supervision fees, which both amounts to 6.27 million each. We would then obtain the total depreciable land capital, which is 72.74 million. The total depreciable land capital would then be added to the total estimated land cost, which is 2.54 million. The total land cost is calculated by estimating the land occupied by each units and facilities in the plant. We would then obtain a new value, which is the total permanent investment, which amounts to $75.28 million. The subtotal is then added to the working capital, which is 11.29 million. Working capital includes indirect labor costs such as construction work operators, administrative staffs. The cost under this section is usually 15% of the total permanent investment. Finally, we will obtain the total capital investment, which is $86.57 million. This is a summary of oil refining annual production cost. The annual production cost is calculated by the summation of total variable manufacturing cost and total fixed cost. The total variable manufacturing cost includes the cost of raw material, catalyst, and total utility costs, which adds up to $163.26 million. The total fixed cost includes total manufacturing expenses and total general expenses. Manufacturing expenses include operation labor costs, maintenance costs, plant overheads costs, tax and insurance costs, as well as depreciation costs. General expenses include selling costs, research costs, administration costs, finance interest, and OSHA costs. The total fixed cost obtained would be $36.85 million. Finally, the annual production cost, which is the total fixed cost and variable manufacturing cost obtained, is $200.11 million. This is a table of product selling price and annual total sales. The total price of each component per year is obtained, and the total sales obtained is $214.45 million per year. This is a graph of cost volume profit analysis, which shows the break-even point. The blue line indicates the fixed cost, the purple line indicates the total sales, and the green line indicates the total production cost. It can be seen that the break-even point for the 1,3-butadiene production plant is at about 71.99 of the production capacity. It is shown from the intersection of the total sales and the total production cost. This is a calculation of return of investment and payback period. The return on investment and payback period is calculated using the total capital investment, which is 86.57 million, and the net profit, which is 13.48 million. The return on investment is obtained is 15.57 of the total capital investment, and the payback period obtained is 6.42 years.
Through this project, we can conclude that fluidized bed catalytic cracking is employed as an alternative method for the production of 1,3-butadiene to overcome the high operation cost of thermal cracking process, at the same time employing zeolite or metal oxide as catalyst. It has the capability to process 1,000 barrels of heavy naphtha per day, or to produce 403,398.72 kilomole of 1,3-butadiene per year. The project location is set at Tanjung Lansa Industrial Estate at 1700 Pasir Gudang, Johor. Several factors are taken into consideration for the plant design. For example, chemical kinetic factor, heat transfer factor, safety factor, and also environmental factor. The annual net profit is $13.48 million. The initial total capital investment cost is $86.57 million. The return of investment ROI is 15.57%. The payback period PBP is 6.42 years. The loss of profit per 1 hour downtime is $3,745 69 cents. The break-even point is at the 71.99% of production capacity. In short, our objectives is achieved.